Okay, so we've been through the process. We've looked at the equipment. We have some idea of what's going on. So what do we do next now? So let us just give some perspective. I sometimes get asked the question, why is the cyclone, the large diameter unit that you see on the picture on the left-hand side, why is it a similar price than a BMW 320i, which is shown on the picture top right? Because the client can see why he's paying that amount of money when you buy the car. When he looks at the engine, he looks at the technology, and he can associate with that. So the answer is as follows. If you look at the capacity of that dense media cyclone, it's a large diameter unit, can process 600 tons an hour. If you look at the yield, and that's for coal, of 50%, meaning then that you recover 300 tons per hour of product. The product value, if it's $80 a ton, and the exchange rate that I've used is $1 to 15 Rand, then it's 1,200 Rand per ton, 360,000 Rand per hour, and the unit basically pays itself back in a matter of less than 3 hours. Thereafter, it keeps on generating money. But there's an important point to notice in this example. The dense media cyclone makes money by the hour, but it can also loses money by the hour. And that's why it's so important that we make sure that this equipment operates as efficiently as possible. Now, just some other interesting information. This is an example of a size distribution, typical size distribution that's going to this dense media cyclone. If you use the 600 tons per hour and you use the size distribution, then that is the particles that it treats. Pay close attention to the y-axis. It's particles per second, not per hour. So this type of information you don't normally see. So the dense media cyclone is making a lot of decisions in seconds. From what I could gather from motor vehicles, the highest number of decisions that I have come across is about 2,000 signals per second that the car receives. I'm not sure if these vehicles of higher values, but the point is just tongue in the cheek. The dense media cyclone, although it's so simple, is doing an immense job. And that's why it's important that we pay attention and optimize the unit as far as possible. Another example. This is Letseng mine in Lesotho. It's renowned for high quality diamonds that's been produced. Some of these diamonds, this is the diamonds that is known to the public that I could find. And these were some of the values that is published. So that's what these diamonds were sold for. Now, it is being processed through this dense media cyclone. This was on a maintenance day. That's why it's looking a bit untidy, but these two units are 800 millimeter diameter cyclones, and the resonance time of a particle in a dense media cyclone is roughly about 6 seconds. So if we take this value of the diamonds, then the processing value per second is quite significant. One can argue more realistically to say, but each second, the total value of that diamond is relevant. And that is true because the time that that material spent inside the cyclone, it's got the probability to be misplaced if something goes wrong. Now, Frikkie has mentioned it, and I mentioned it earlier, that your system consists of a couple of factors. We've talked about the ore characteristics. Frikkie on the previous presentation talked about the cyclone design. And then there's the plant operation and the medium characteristics. That's also all coming together for the optimal performance. So if we start talking about best practice, it's a word that's easily used. But what is best practice now really in this context? You need to understand how the cyclone operates. Now, I'm specifically referring now to the dense media cyclone. We also need to understand how the equipment before the cyclone operates and also after the cyclone. What makes it, what conditions is required to have optimal performance? And then what process factors affects all these type of equipment to have a complete understanding of what's going on in your process. In this flow sheet, of which you only now see pieces of equipment, you've got the following streams. You've got the ore stream coming into the process from the feed side on the left-hand side, and it exits the process in terms of floats and a sinks fraction. You've got the correct media circuit, where the media is being that's used to do the separation. You've got your water addition circuit. You've got your dilute media circuit. That's where the media and the water has been mixed, and you need to recover it. And then you've got your fresh medium addition, which can be ferrosilicon in this example or magnetite. Each of these streams has got the ability to influence eventually the performance of the dense media cyclone. And the focus is normally only on the cyclone. So whenever there's inefficiency, that unit gets blamed. But people forget that there are other process streams, and we need to make sure that those process streams is maybe not the cause of this problem. So I'll now go through each of these equipment, talk about some of the factors that I've come across over the years. But for you as the viewer, I believe that there will be other factors as well that I haven't thought about. So you're more than welcome to comment or send me a mail if you feel there's something that I've omitted that also needs to come onto this list. So let's start with the feed coming into the process. A change in feed rate can overload the equipment, and it can change the media to ore ratio. Now that sounds obvious, but yet in processes that happens. Large processes, high throughput processes or plants normally have fairly consistent feed rates into their process, but smaller plants do not always have that capability. So now as that fluctuation gets into the process, it then overloads some equipment systematically. And one of the things is then when you have erratic feed over your desliming screen into your mixing box, then you can affect the media to ore ratio. A change in the feed size distribution can affect the solid split and the feed size distribution, the optimum feed size distribution to the cyclone gets distorted. If you've got a coarse and a small DMS circuit, then that split starts to get altered. And then one piece of equipment will get a lower a lower tonnage, and the other one a higher tonnage. And there the disturbance starts to occur. A change in material type can also affect the equipment. And in this example, clay. There are operations that you get clay balls getting into the process. It doesn't break down completely. It actually gets into the cyclone still in the form of a clay ball, and then it stays in that cyclone, and that clay ball grows to the extent where they eventually have to drain the cyclone because it can't get out. So those are some extreme examples, but when that starts to happen, one has to relook at your process, see what needs to change, what can be altered. The change in the washability of the material coming into your process can affect the dense media performance, because more relating now to the spigot capacity, is that if your yield all of a sudden becomes quite low, in other words, in coal, a low yield means that there's a high sinks fraction that's getting to the spigot. If you design the cyclone that is almost or that there's just enough spigot capacity left and there's a change in the washability characteristics, you can run into an overload situation. So one needs to be aware of what's coming into your process. The amount of near gravity material can affect your DMS efficiency and yield. Near gravity material is material that is situated around the cut point of the cyclone. Normally, if your cut point is 1.5, for example, in all the material between 1.4 and 1.6 is defined as near gravity material. Sometimes it's between 1.45 and 1.55, depending on what definition you choose to use. But the higher that amount, the more difficult it becomes for the cyclone to make a decision. And remember, the cyclone's got limited time and it needs to do a lot of decisions or make a lot of decisions in a very short period of time. So that is now some of the factors on the feed side that needs to be taken in consideration. On the desliming screen, a change in feed rate can overload the screen, resulting in fines misplacement. I've shown you a picture in the first presentation, where if the screen cannot screen out all that fine material, it now reports into the mixing box and to the dense media cyclone. And you've seen Frikkie have shown the effect of the breakaway size, and also, so the cyclone cannot beneficiate less efficiently the finer fraction. So that fine should have gone to a different process that is designed to process that fines more optimally. If you overload your desliming screen, we create a problem. The screen panel wear on the desliming screen, that can also contribute to a mass split difference. So you start to then send more coarser material to the underpan, and it goes to a process that's not suitable to treat that coarser material, while the dense media cyclone was the right a piece of equipment to process that material. The amount of wash water, sometimes it's a volume imbalance, and people cut back on the wash water on the desliming screen. Then you do not operate efficiently on the desliming screen. You are not sending the right quality of material to the dense media process, and thereby we can induce some inefficiencies. And then you've got the other side of the coin. When there's too much water, or if there's pegging in the panels and your drainage rate gets affected. Now you have some water that is not draining through the panels, but it's carrying over on the screen discharge end. Now, what's the implication of that? The media that enters into the mixing box, where your media that's at the correct density, you decided that's the media density that needs to mix with the ore and it's on its way to the cyclone. That control mechanism sits before the mixing box. The material that's entering from the desliming screen goes into the mixing box, and if there's water coming with, you are introducing additional water into the media, which no one knows about, and you are sending the wrong media density to the dense media cyclone. So that is something that very subtly happens, and people don't always take note of that. Then, if we look at the dense media cyclone, we've talked about some of these factors, and there's going to be some repeat based on what Frikkie was also presenting. A change in the cyclone feed size distribution can affect the overall efficiency. That comes back to what Frikkie the previous presentation was all about on the breakaway size. If you send the wrong size fraction for which the unit wasn't designed for, then inefficiency starts to occur. If that situation happens, discuss it with your supplier. Just make sure that that equipment is still adequately or suitable for that process. The change in feed rate can affect the media to ore ratio, because some cases the media pump is a fixed speed pump. Now the pump only pumps at a constant volume, and if the feed rate into the plant increases, there's no ability to increase then the speed of the pump to be able to pump more media as well. So some of the media gets displaced by the ore coming in, and they change the media to ore ratio. So just increasing the feed rate, just for the sake of trying to get more money out of the process, be careful. Make sure you know the consequences. A change in the feed rate that can affect the spigot loading if you've got low yield material. When there's a lot of load on the spigot already and you increase the feed rate, you can push the cyclone in an environment where it starts to become inefficient. It's not necessarily meaning it's going to overload the spigot, although it's not impossible. But the ratio, there's a ratio of media to ore also relevant for the spigot. And the more ore is going through the spigot, the less media is present going through the spigot, and you reach a point where inefficiency starts to occur. So although your cyclone discharge may still be flaring, it doesn't mean that you are operating in the correct media to ore ratio. The change in top size can impact on the cyclone inlet opening. This situation has manifested itself before in a case where a plant needed to increase their throughput by opening up crusher settings. That larger material went into the dense media plant, and that resulted in blockages starting to occur because each cyclone has got a certain limit. The cyclone presentation by Frikkie showed that you've got 3 times the particle top size. If you start to exceed that, you're playing with fire. Now, one of the things is they can say, well, we can make the cyclone larger. But a larger cyclone requires larger volumes, and now you need to check the whole process if it can accommodate this deviation. A change in yield can also impact on the spigot capacity. Very similar to when you've got the increase in top size. As the yield change, if you've designed your cyclone to have a certain amount of yield or floats reporting to the overflow, and that amount becomes less, again, you can run into a spigot overload situation. Know what material you are treating. A change in pressure can affect the media to ore ratio. So if you increase the pressure, you obviously pump now more volume. If it's still a constant ore feed rate coming in, then you need to add more media. That's a good situation. But just keep in mind that speeding up the pump does have implications because you're also pumping more media to the cyclone, and more media leaves the cyclone. And that goes then onto other equipment that has been designed based on the original amount of media flow rate. The differentials inside the cyclone is going to change as you increase the operating head, as you increase that driving force going into the cyclone. The media classifies differently, and as that media classifies differently, the differentials, the difference between overflow and underflow density change. And as soon as those two values start to drift or change, your cut density has changed as well. So it's not only the media set point that controls the cut density, but one of the factors is the operating head. Worn spigots, that spigot to vortex finer ratio that was shown in the cyclone's presentation. As the spigot becomes bigger, the efficiency starts to drop off. You can install oversized spigots. We'll talk about that later in this presentation, what exactly that is. So there's ways of making sure that you don't have to run your spigot for too long. High near gravity material. Again, that's the material that sits around the cut point of the cyclone. It requires more attention time. One way of doing that is to install a barrel section, make the cyclone longer, but you can only do that if your installation allows for that. It's not impossible, but it's difficult. But that's one of the things that you can also consider if there's a high amount of near density material coming into your process. So depending on the amount of or the type of material and the quality of the material, there's ways of making modifications around the dense media cyclone. It was also shown in the previous presentation, the inlet, you've got different inlet openings, different vortex diameters that you can incorporate. But each one of those differences impacts on the volumetric flow rate going to the cyclone. And that's going to impact on the equipment that's present in your dense media process. Just keep that in mind before you start making a change around the cyclone. Because suppliers will say, yes, sir, we can help you. We can make those modifications. But just know now, there is some other aspects that you also need to consider. Then access to the feed and overflow streams to sample the media. The differential that Frikkie was talking about between the feed and overflow, that's what we use to define, to determine if the cyclone is operating correctly. There's also the overflow and underflow that's used more so on coal and in areas where you can access the spigot between the overflow underflow, the overflow underflow differential. That's got a different reference between 0.02 and 0.05. But most of the times we use the feed to overflow. And the reason for that is because in diamond mines, you cannot get access to the spigot because that's where the diamonds is. So we had to develop a different way of calculating the differentials. But you must be able to access those streams. There was a situation where there was a pilot plant being built because the client had already exactly the same one. The second one didn't perform as the first one, and the engineering house wanted to know why was that the case. And we said, well, just give us the feed and overflow densities that we can have a look of the media to see what's happening. And they couldn't. And they went to other specialists in the field because they thought that we were wasting a bit of their time. And those specialists asked the same questions. So if you cannot access those streams, it sounds like a very simple thing, but that information is extremely valuable. So that's on the cyclone itself. Then on the drain and rinse screens, the amount of spray water that obviously can affect the media usage. That's again, if you lose media, you lose money. And then the quality of the spray water. It's not quite common, but sometimes people use dirty spray water, and that just aggravates the amount of non-magnetic material present that is going to the magnetic separator, because the water in the drain section, on the rinse section of the drain and rinse screen, that is on its way to the magnetic separator. But the magnetic separator has got certain requirements as well. Poor screen drainage can affect the dilute medium circuit performance, meaning by that if you can't drain all the media on your first section, it's going to run over to the dilute section, and now there's a higher load on the magnetic separator. Different screen apertures between the drain and rinse screen and the desliming screen. There was a situation some years ago where test work was conducted on the desliming section of a coal processing plant, and smaller apertures was tested, and the recommendation was to do a partial test. The whole deck was unfortunately converted, and that resulted in the desliming screen having aperture of 0.03 and the drain and rinse screen having an aperture of 0.05. And in between, there was a missing fraction that started to build up in the process. And that resulted eventually that the dense media cyclone started to become inefficient. And the client thought that it was the cyclone's fault. Then worn apertures that can cause buildup of non-magnetic material. The same again as if you don't look at the drain and rinse screen maintenance. You are sending more non-magnetic material to the magnetic separator, but also there's non-magnetic material building up in your medium circuit, in your first portion of the screen, because that stays in the circuit. You just have a bleed off that we talk later about it, but most of the media stays in media circuit. And if there's non-magnetic material starts to build up, then it starts to create changes in your media characteristics. Then on the densifier, and later in the presentation I'll talk a bit more on the densifiers, but because this densifier are small diameter units, you can have blockages if there's foreign material in the feed line to the densifiers. And as soon as the densifier gets blocked, your water removal ability is reduced, and that can have then problems with density control if you can't get rid of all the water or some of the water in your circulating media sum. And because the overflow goes to the dilute circuit, all of a sudden there's more magnetic material going onto the magnetic separator section. A poor bleed, if you don't bleed enough of the media out to the dilute circuit, then you can have a buildup of non-magnetic material. And the quality of the media deteriorates, and that starts to affect the performance of the dense medium cyclone. The use of a pipe densifier or cyclone densifier depends on the type of media. And I'll talk later about the differences between the two. But densifiers, there's specific densifiers for specific applications. And then whatever densifier you choose, that can also have an impact then on the selection process for your magnetic separator. So if you start to change densifiers in an already designed plant, make sure then that you just check the rest of the process as well. The densification that you can achieve in your process can be done via 3 methods. You don't always use all 3, but just for the sake of clarity, I'll put it all in one flow sheet. You can have your normal bleed. Every plant do have a bleed section where you take some of your correct media and you bleed it deliberately into your magnetic dilute circuit sum. So that was most of the times the only system that people use. But if you need to remove a lot of water, you cannot always bleed enough of the media out. And this bleed is not always constant. You bleed as you require to remove water, and that puts then again a bit of load on the magnetic separator. You've got a dilute densification circuit. That's normally used on smaller plants where you try to save on equipment, because you use the pump to the cyclone, and then you can just gravity feed on the magnetic separator. And then you've got your correct media densification. That's the recommended method that we would, I think that's the most effective one. But either one or 2 of these 3 are normally always present in the process. And if you don't bleed correctly, then your media characteristics can get affected. On the magnetic separator, your magnetic separator is sized on a volumetric flow and a magnetic loading. So if those factors change, then it starts to affect the magnetic separator efficiency. If you've got poor maintenance on your magnetic separator, then you also affect the magnetic separator efficiency. And poor level control. And sometimes the magnetic separator is encapsulated with a safety cage. So you can't see if the levels is correct or not. Yes, you can install instrumentation to monitor that. Very important, do monitor the level and have proper maintenance on your magnetic separator. Because, and then there's the high concentration of non-magnetic material. I said to you, the volumetric loading is one area for design. And then the grams per liter of magnetic material. So if you have a high content of non-magnetic material, it starts to affect the performance of the magnetic separator as well. And here's the thing. If the magnetic separator is not operating efficiently, then it starts to lose the finer fraction first. Your media becomes progressively coarser, and that leads then to a different behavior inside the dense media cyclone. And that's the reason why the measurement of differentials is so important. We start with that to determine, is the media still behaving correctly? Because if the cyclone gets blamed and we do the differential calculation and we see the media behaves differently, then most probably the cyclone is not the problem. Your problem lies somewhere else in the process. The advancement in magnetic separators, I said earlier, also leads to stronger magnets being developed. I just need to check that it doesn't entrap non-magnetic material, too much non-magnetic material in the magnetic fraction. Don't think it is a common problem. It's just something that may have the probability of happening. And then even with self-leveling magnetic separators, you still need to monitor the volumetric flow rate and check that oversize is not getting into the magnetic separator so that it doesn't damage the drum section of the magnetic separator. So that's some comments around the magnetic separator. So we've talked about the ore characteristics, the cyclone design, and we're busy with the plant operation. And one of the other factors, medium characteristics. So Frikkie alluded to that as well in his presentation. The quality of the media and the size distribution of the media can affect the cyclone behavior. On most of the coal plants, you normally have 1 or 2 grades of magnetite. Frikkie has shown there's 3 grades. In South Africa, normally there's only 1 grade commonly used, to my knowledge. But on ferrosilicon, there are various grades. And those grades are associated with the operating density and the cyclone diameter that's going to be used in that application. So the operating density normally don't generally change, but sometimes people change the cyclone diameter. They want to increase capacity, for example. And they don't change the media grade, and now there's a mismatch, and the cyclone starts to behave differently, produce different differentials, and the client then wants to know why has this happened. Just want to reiterate the quality of the media. You get cheaper media across the world. Be careful. Some of that media can lead to a different behavior in the cyclone. Just if you have changed media suppliers and there's a change in cyclone performance, look first at the impact that the media might have had. Don't immediately blame the cyclone supplier for supplying poor equipment. It may not be the equipment. So on this magnetite grades, as I said, here I show two grades. Frikkie has shown a coarse grade as well. But that is the type of options available, and it is referring specifically to what operating densities you want to then use in your process. So the grade is related to the operating density, and it also just shows you then what is the expected underflow densities. These are just guidelines. And then on the ferrosilicon, again, certain media types for certain operating densities, and then obviously the associated underflow densities that you can get from that. Then you have situations. If you look carefully, the maximum density on magnetite, and showing in this table, is about 1.9 operating density. For ferrosilicon, the lowest is about 2.3. So what do we do if we need to operate in between? And that is a bit of a conundrum, because the only option you've got is to blend magnetite and ferrosilicon, because you can't only use ferrosilicon because there would be too little. The solids concentration will be too little in your feed to the cyclone, so the media becomes unstable. You can't use too much ferrosilicon, magnetite, because now you increase the solids concentration too much and get viscosity. So people blend it in together, and if you know what you're doing, you can get away with this. There are operations that operate like this. But keep in mind, when you go now to your magnetic separator, the ferrosilicon and the magnetite has got two different magnetic susceptibilities. So the ferrosilicon is normally the stronger one. So the magnetic separator will recover all the ferrosilicon, and whatever, if there's space available, it will recover the magnetite. Maybe it's not so clear cut, but I think you get the picture. Progressively, your magnetite is at the back end of being recovered. So if that starts to happen, then you start to lose progressively more magnetite out of the process. Now your ratio of magnetite to ferrosilicon has changed, and you need to be aware of that. And that comes back to be able to determine differentials, because if you measure your differentials and you know what you're looking for, you can detect those deviations and take corrective actions timelessly. Then accurate density control, because that will affect the yield, of course, and the efficiency, especially if you've got high near gravity material. But how often do people check the accuracy of the density control? Sometimes what the scale, that density scale that you use to calibrate the density scale, is that scale correct? Has it been calibrated with water? Those are sometimes small things that you think, but people should know about it. It's actually a no-brainer, yet it does happen in the process. And once you calibrated your densitometer to the wrong settings, then you won't know until you see that you're starting to lose money from the process. Then this was now a discussion just on some of the equipment inside the process and how it impacts overall on the dense media cyclone performance, and sometimes on other pieces of equipment in the process as well. But everything is linked. To minimize the medium losses, some guidelines. You don't overload your magnetic separator. In other words, you need to be able to measure, sample the feed to the magnetic separator, know what that equipment was designed to do, make sure it maintains that conditions. You need that constant overflow of the magnetic separator. Enough water on the screens. Make sure that the spray is covering the whole screen. Again, you sometimes go to plants, you talk to people about this, they say, yes, I understand. You go into the plant and you see the screens, the spray is not operating correctly. Make sure that the spray nozzles are not blocked. And some of the water that is coming from your magnetic separator effluent is being recycled back into the process. And sometimes there's large particles present that can block the spray nozzles. Minimize spillages, leaking pumps. Prevent spillages and splashing as far as possible. Yes, good housekeeping. That will help to save media. And then wherever possible, power failures. That's now relevant to applications or processes. That's in areas where they do experience power failures on a regular basis. So that's not applicable to all the plants. You do have ore bodies that sometimes can add to medium losses. Porous gravels, magnetic gravels, clays gravels. That is a bit difficult to make sure that difficult to optimize the process. Then the only thing you can do is to do your best to minimize the losses as far as possible. Now, we talked about the separation curve. And in this case now, the curve is shaping to the other side. It's recovery to underflow. So we know that we want this slope to be as steep as possible, and that's what we refer to as the efficiency. Just for clarity, the reduced EP that you see on the screen is a normalized EP. That's when you want to compare different dense media cyclones or dense media vessels, for that matter, in terms of performance with each other. What you do is you remove the effect of the operating density, and then you can comment on the performance of the unit. The point on this slide is just that we focus a lot on the efficiency, but it's no use having the optimal efficiency if your cut density is not at the correct position. We've talked about you've got a control set point that you can via your SCADA system program into the system. That doesn't mean it will always stay at that point. So some of the next slides is just some of that you'll find a repetition from what Frikkie was saying, but just to reiterate again the importance of the cyclone itself. And then talking onto the cut density deviations. So the main parameters, top size and size distribution. Operating head. We talked about the media to ore ratios, efficiency, but the operating head or the operating pressure can impact on the cut density as well. It can change the cut point inside the cyclone. The change in medium to ore ratio can impact on the cut point of the cyclone. Recovery to spigot, your mass yield, that impacts on the spigot diameter. And to a smaller extent, it could maybe impact on the cut density as well. Your medium quality, definitely impact on the cut density. If you've got a very coarse media, you're most probably going to have a larger offset between your operating media coming into the cyclone and the actual cut density. Argument's sake, if you're operating at 2.6, your cut density may be 2.8 or 2.9 for that example. If you've got a very fine media, then you've got 2.6 operating density into the cyclone and maybe a 2.7 cut density. So that's where the differences start to come in. And then constant operations. Just for clarity, your inlet is that's where the top size affects the cyclone design. Your feed media quality also impacts on the operation of the cyclone. Your cyclone diameter is where the media to ore ratio, the capacity of the cyclone come into play. The operating head and then your spigot diameter, that's related to your mass yield in the operation. If you want to have a constant operation, pressure gauge, install a pressure gauge. Many operations do not have pressure gauges or they don't have working pressure gauges. Now, the thing is, the pressure gauge can indicate if there's fluctuations in the process. You cannot look at this, I cannot look at the cyclone and see fluctuations sometimes, while the pressure gauge can pick it up. Very valuable tool. Check the spigot diameter. We normally recommend the spigot diameter to wear up 10% of the original diameter. Then it needs to be replaced. Now, here's the problem. Is that maintenance people say, but this is stupid because there's still wear material available. Let's use the spigot further. There's a change that's starting to happen inside the cyclone. The bigger spigot starts to affect your cut density. People don't always know about that. It doesn't mean that you cannot use the spigot for a longer period of time, but know now what can happen, measure the change, the performance of the cyclone, and just be prepared. If you can accommodate that, use the spigot for a longer period of time. Otherwise, it's recommended that you change the spigot after 10% wear. Check the plant feed conditions, constant feed rates. If you've got surging sumps, that's either surging or overflowing, there's a volume imbalance. Surprisingly, people sometimes live with these surges, but it's not surging sump to a dense media cycle is not a good thing. If the sump is overflowing, obviously there's a problem somewhere else, and one has to just make sure if the cyclone is maybe not part of that problem. Misplaced floats to the underflow. That's when you have a worn spigot. Too low media to ore ratios, your medium viscosity or inadequate operating head, like Frikkie was saying. And then misplaced sinks, that's going to the overflow. That's when your spigot can be too small. Your vortex finder can be damaged. People don't always think about this. Your media can become unstable, or you can have inward steps in the unit itself. In terms of the spigot on the top left-hand side, worn to distraction, chances are that you've exceeded the limit of vortex finder to spigot ratio. And again, that starts to impact now on the efficiency of separation. And if your circuit can accommodate this, the poorer separation efficiency, if you don't lose any money or little money, that's acceptable. But most of the operations can't tolerate that. You do get sometimes spigots that's flaring on the outside. It looks like it's worn. But just keep in mind, if the internal diameter is still as per specification, you can still use these type of spigots. I talked about oversized spigots. When you design, when we supply cyclones, and all suppliers do that, you've got your slight outward step. You've got your cone, your spigot, and then a slight outward step. But now, if you replace the spigot, and you replace it with the standard original spigot, you can generate an inward step because the cone section has worn thinner already. So when you put in a standard spigot, the diameter at the top of the spigot is smaller than the lower, the diameter at the bottom of the cone. That's where the oversized spigot is coming in. The diameters is the same exit. The exit diameter is the same, but it's the top diameters that's different. That is a valuable option to extend the life of your dense media cyclones. The equipment before the cyclone, again, we've talked now in the overall process just now. So some of this is again some repetition, but it's again deliberately done like this to drill this into the mind of the viewer. Your screens, if you overload your screens, the fines carry over. Something to keep in mind. That can increase the media viscosity. Because if you carry over fines, there's also ultrafine material that is going to be smaller than the apertures of your drain and rinse screen. And in the drain section, that fine material is now going to start accumulating. And there goes the medium viscosity. Decrease in the medium to ore ratio, because you are sending more tons now to the mixing box if you overload your screens. And then this breakaway effect to keep in mind. Spray water, too much. If you have too much spray water, just keep in mind, every screen has got a certain drainage capacity. Don't overdo it, but just keep in mind that you don't have too little spray water as well. And then too much spray water can carry over into the mixing box, lowering the medium density. Sump level control, just ensure that we have constant flows. And then the pump speeds, make sure that the pump and the cyclone is matched. Sometimes people change pumps due to a breakdown and there's a mismatch between the pump and the cyclone, and then it starts to affect the cyclone performance as well. Equipment after the cyclone, the drain and rinse screens, too much medium carry over. We've been over that. It's placing load on the magnetic separator. Do not underestimate the importance of the magnetic separator. Too little rinse water results in medium losses. And then improper densifier operation, if you've got densifiers in your circuit. If it doesn't operate correctly, it also can impact on the cleaning of your media and the density control. Magnetic separators, preferential loss of the fine material. As I mentioned earlier, when the magnetic separator starts to become inefficient or is starting to be overloaded, the fine fractions get lost first. That can impact on media stability. It can also result in media losses if it's not operating correctly, and then poor cleaning if a magnetic separator is not cleaning the media properly, you can start generating viscosity problems again. This comes back, you must be able to access the magnetic separator as well to do some measurements to see if the unit is operating correctly or not. Then in terms of sampling around the dense media cyclone, ensure that this is now relevant for operations where you can actually sample the material and analyze the material. Most relevant for coal. On other commodities, you use HLS separations. Quite expensive, time consuming, and some of the operations don't do that. But wherever you are going to sample around the dense media cyclone, ensure you've got a proper sampling points, access to proper sampling points. Make sure that you can obtain a representative sample. No use taking a sample and it's not representative, because you're spending time, money, and people power, and if the sample is biased, you're getting results that's of no use. Calculate the differential. So when you sample around the cyclone, you also need to sample the feed media and the overflow media for differential calculation. That goes hand in hand in analyzing the results. Your feed, overflow, and underflow samples, that's required for the cyclone evaluation. You can't just have 2 of the 3 because you need to determine then the overall EP. More than one set of samples if possible, because that is verifying repeatability. Operating pressure of the cyclone, very important when you do analysis around the cyclone, evaluating the efficiency, check the pressure, because if you get strange results, that's one of the parameters that suppliers would refer to see if there's not a problem. The internal dimensions of the spigot and vortex finders is required during that operation. And then if possible, if there's a cyclone description, we can, that would also be useful. And then the feed rate to the unit. This is the type of information that's required so that you can then evaluate the efficiency of the cyclone to the best of your ability. When you sample and using a Marcy scale, as I mentioned earlier, make sure that the Marcy scale is calibrated. Don't just take a sample and assume that it's right. Again, people think it is so basic, it's not worth mentioning. You will be surprised. The second aspect is the Marcy beaker. It's got 2 holes on the side, so you will close those 2 holes, dip the beaker into the media, and remove it. Some cases, you then walk over and put it onto the scale. If that is the type of activity that you're doing, you've got a problem, because while you're walking, the media starts to settle out. By the time you've removed your hand to drain that to the correct level, you're only draining off water, and there goes the accuracy. That's especially relevant when you're calibrating your densitometers. You take the sample, remove your fingers, drain it, close it again, and move on to the scale. Sometimes you may not be able to sample, or do not want to sample from the discharge of screens. So you want to sample individual cyclones. The red lines just indicate how to sample through the streams exiting the cyclone, if ever you want to do that. Some of the reasons why you want to do that, if you've got multiple cyclones discharging on the same screen, if you sample on the screen and you get a poor result, you will not know if it's all 3 cyclones that are producing that poor result, or is it one of the 3 cyclones. And that's where you then need to then you need to sample individual cyclone or the cyclones individually to assess if it's not one of the cyclones that's giving a problem. In terms of where, proper inspection frequencies is required. I think that's most common for most operations, but people sometimes tend to push operations, especially when the commodity prices is quite high. People don't want to stop, and then you start to push equipment into the danger zone. Proper accessibility for inspections. Sometimes you've got the underflow boxes and overflow boxes, and you cannot get access to the cyclone. It's bolted with a huge number of bolts, and metallurgists don't have the time, or maintenance people don't have the time to loosen all those bolts, so they ignore it or they leave it. And then you don't inspect the cyclone. If you want to operate a cyclone till destruction, be careful because it's expensive. Your efficiency starts to deteriorate, your car density starts to drift, and then you have an unplanned failure as well. And it costs money per hour to operate the plant, or you're making money per hour. So if your plant goes into a stoppage, you're losing money unplanned. And then the wear locations on the cyclone depends on the type of commodity that you're treating. Most of the commodities, you have highest wear at the spigot, and it works its way up to the cyclone. But in other commodities, like in diamonds, you have a very low mass yield to the spigot, so most of the wear takes place inside the cyclone. People sometimes ask, what must the wear pattern look like inside the cyclone? Now, this type of pictures is where you've got excessive wear. This starts to affect the cyclone. So you need to replace these parts. But sometimes you have a slight groove that forms inside the cyclone. So as the material flows through, the smoothness of that groove results in the efficiency of the cyclone not being compromised. But these excessive type of wear patterns, again, it's objective. So most of the time suppliers will say, just send us a photo, or you will inspect it yourself just to see how severe the wear is. But slight wear patterns inside the dense media cyclone is not a problematic situation, but these tend to be. We've talked about the fitting of the oversized spigot, but make sure that you use the correct parts and not used parts, because new and used parts sometimes don't align correctly, and then you have inward steps. So proper alignment, very important. And then if there's a incorrect fitment, you can get now a localized wear, but you can also misplace material. In this example, the green item is the spigot, and here's the cone, and it has been misaligned. And that is what the spigots look like. So the life expectancy has been shortened because you have more wear on the one side of the spigot. But during this operation with that inward step, material that should have gone to the sink section has been diverted back into the cyclone operation, and most probably a portion of that sinks has now gone into the overflow of the dense media cyclone. Then on tracers. Now, when you can't sample around the cyclone with material, people use density tracers. So density tracer is just a synthetic type of material made to a specific density and a specific size, and that needs to represent the ore that the cyclone is processing. So it's a quick assessment for efficiency, quite easy to conduct, and as you see, it's quite cost effective. It saves time, it saves personnel requirements. No hazardous chemicals used, but just keep in mind, when you do tracer tests, normally it's been done with off-ore conditions. You don't get the full picture. There are now tracers these days, radio tracers that you can throw in with the ore. Quite useful. I think it's a bit expensive, but some operations have used that and get interesting data from that. Just keep in mind that the tracer test is just giving you results of the cyclone performance without ore. Doesn't mean it can't be used, or it also provides valuable information. When you are looking at the amount of tracers, that's where one of the question marks come in, is how many tracers do we use? Now, a guideline is when you're going to look at the areas of your upper and lower density ranges, then look at 0.1 density intervals. But as you get closer to your car density, those intervals need to be made smaller so that you can get more data to complete your partition curve. But know what you're looking for. What size of interest, what size are you interested in? What do you want to determine with the tracers? And then also think about what can be practically recovered. What size tracer? The smallest I'm aware of is 2 millimeters, I think. But it's quite difficult to recover that as well. Then another question is, how many tracers do we use? Because you've got now different density tracers and different size fraction per density, it becomes quite extensive. So people try to stay with a small amount of tracers as possible. This graph just illustrates that the more tracers, the more accurate your results. But it becomes quite excessive when you look at the higher values. So around 50 to 100 tracers per density and size range, that's more or less what I would think is recommended. I think 100 may be already a bit of a challenge. 50 could be a good starting point. In terms of density control, the picture on the left-hand side shows a fluctuating densitometer. On the right-hand side, what you then get is you get a cyclone that's operating quite acceptably, but it's operating at different cut densities. Now you sample across that cyclone over time, and you get the black curve. And you say then that the efficiency of that cyclone is poor. Maybe it's not poor. Maybe it's the density drift that was the problem. So it's also applicable when you've got multiple modules. If you sample your overall process with individual modules in between, you may get something similar like this. Because if the modules operate at different densities, then you're going to get different partition curves of these operating modules. And then it looks as if the plant is not operating correctly. On the distributed design, there's different designs. Sometimes you want to use you have to use multiple cyclones and not a single cyclones. There are different options: tangential, T-piece, Y-piece, and a pulp distributor. If you've got tangential inlets, you can get a bias distribution. Even with T-pieces, it's also not optimal. When you look at your Y-piece design, the problem with a Y-piece design, if there's a bend before the Y-piece, you start to get a problem. And then a pulp distributor, proper design pulp distributor, if you have the bend perpendicular to the outlets, you get proper mixing. That's the best type of design that best option that you can have. If there is multiple outlets, speak to the supplier to find the best orientation. In terms of densifiers, just quickly, the densifiers is there to remove water. So whatever water is coming into the feed, some of this water end up in your correct media circuit. You need to remove that water. So we talked about correct media, dilute media, and correct medium bleed. When you are looking at those bleed systems, we talked about was the dilute densification, media bleed, correct media bleed, and correct media densification. You can use a cyclone densifier or a pulp densifier. A cyclone densifier produces higher densities for your correct medium circuit. But because it's doing that, there's a higher amount of volume going to the overflow, meaning there's more media going to the overflow. So there's a higher risk of media losses because it goes to the max step, and the max step is not always 100% efficient. But when you need to change your densities quite often, a cyclone densifier is normally the recommended option. Pipe densifiers, when you run more consistently with operating densities over a longer period of time, a pipe densifier is the more recommended option. It's got a lower water removal ability, but also it means then that there's less media going to your max step that can be lost. But because it's got a lower water removal ability, it's used for these operations where you have more stable, more consistent operating densities over a longer period of time. You don't need that high operating or that high density in your correct medium sump because you're not going to change densities so often. The operating, when you're operating densifiers, we work on 10 meters head, 10 meters, 10 meters physical head. We don't relate it to the cyclone diameter or the pipe densifier diameter. It's physical 10 meters. It can be gravity fed or it can be pump fed. Densifiers, if you only use it, those who use densifiers in the operation, some people use it during startup only and then they stop the densifiers. That's a problem because your circuit normally never stabilize completely. There's always some non-magnetics that's building up in your system. Continuous operation of densifiers is what we recommend because then you continuously remove water, you continuously remove non-magnetics, and the system then starts to stabilize. So densifiers reduce startup time, more accurate density control, reduce magnetite losses. Can also be used on ferrosilicon plants. It doesn't mean that you have to use densifiers, but it's an option to consider if ever you've got a problem with your density controls. So in conclusion then, this whole presentation can be summed up in the following then. When there's a problem, you start with the cyclone. Look at the internal obstructions, look at the capability of the equipment. What does it look like? What is the internal conditions? Is there any grooves, misalignment? Is the instrumentation on the cyclone correct? Once you finish focusing on the cyclone, you stand back and you then look at the operational side of the cyclone. The feed rate operating it, is there surging? What's the differentials looking like? What is the particle misplacement? Is there any particle misplacements? That is now looking internally in the cyclone, then looking at the operation of the cyclone, and then thereafter you stand further back and you look at the overall process. What's the levels in your operating in your head boxes? Densified operation, quality of the media, density control, feed rate, plant feed rate. Is there maybe air entrapment and the auxiliary equipment that is present in the process? And if that is also being optimized and sorted, then you have the optimum dense media circuit. I thank you.